First off, in my shopping cart question, it says we're pushing a shopping cart with 30 newtons. That makes it accelerate at 4 meters per second squared. There's enough there that we can backtrack and figure out the coefficient of friction. In hindsight, I shouldn't have called it a shopping cart. Shopping carts, their wheels roll, so the coefficient of friction is a little bit different with those. So the physics we'll do it the way with a free body diagram like you've been doing the questions, but technically shopping cart's not the best thing. Think of this more as like a crate or something that would slide across the ground, as opposed to something with wheels that would roll. Other than that, hopefully some of this is becoming a little routine. We're always going to start with a free body diagram. Gravity straight down, normal straight up. It doesn't say anything about this thing flying into the air or being on a hill or an elevator, so that's what I call the boring case. The normal force is exactly the same as gravity. Gravity is always mg, so that means the normal is mg. Horizontally, we're pushing it forward, and there's some friction fighting us. That means when we set up F net equals ma, since our pushing force is winning, is the larger force, I'm going to make that the positive one. So I'm going to say Fa minus Ff equals ma. Ff is always mu times Fn. That's going to be equal to ma. Since it was a boring case, I can do one more substitution. Fn is the same as mg. That's going to be equal to ma. The way this particular question is set up, we now know everything except the mu. The Fa was given as 30. Oops. The Fa, there we go, bring it back. The Fa was given as 30. I don't know what the mu is, but I know the m was 6. G is always 9.8. The m was 6, and the question says it's accelerating at 4. When we flip-flop things around, we get mu times 6 times 9.8 is 58.8. The 6 times 4 is 24. We end up with 30 minus 24, so we end up with 6. When you do the division to finish it off, the mu works out to be roughly 0.1. While we're at it, we'll do 2 this time. A similar question, we've got, this time I did better, I called it a crate. A crate on the ground, we're going to push it so hard that it'll accelerate from rest to 2 in a distance of 4. This question is very similar to the last one, just I didn't give you the acceleration. We're going to have to do a little bit of work first to find the acceleration. So if we start with that, it said that it started from rest at v1 of 0. It got to a speed of 2 meters per second in a distance of 4 meters. We're going to use that to find the acceleration. Think back to Unit 1 stuff. We don't care about t. The equation that matches that is the one I call the difference of squares equation. We know that 4, excuse me, 4 equals, 4 equals 2 squared minus 0, all divided by 2 times a. I'll let you do the algebra on that, but as we flip things around and solve for the a works out to be 0.5. Now the question is a lot like the one we just finished. Free body diagram is going to look the same. We've got gravity straight down. We've got normal straight up. F applied pushing it. Friction fighting that. Doesn't say anything weird, so it's a boring case, so the normal is equal to gravity, which means the normal is equal to mg. In the horizontal, we've got a tug of war, so I'm going to set up F net equals ma. The F applied is winning that tug of war, so it's the positive force minus Ff equals ma. This time, actually it's a little bit different than the last question. We know that we're solving for Fa. We know the mu is 0.4, so it's similar setup, just a different question, different unknown. The m is 8, g is 9.8. Oops, I kind of did that step in my head here. Let me blow that up. M times a, the a, we did the math to get 0.5. The step I did in my head was kind of in here. Ff is mu Fn. And as we've seen, that turns into mu mg. So that's where that came from. In this line, we know everything but F applied. I'll let you do the algebra, but when we multiply it out, flip the 4 times 8 times 9.8 to the other side, add it to the m times a, we get an F applied of 35.4. If you look back at this one, this is really probably as hard as I could make a question. You had to do some kinematics to start to find the acceleration, then use logic to know the normal force, and then crunch it out to actually solve the problem. So this one here is probably as tough as I could make it.